Hello dear students, welcome to my YouTube channel. This is Joginder Rohila and today in this video I am going to discuss with you about crystal field splitting in octahedral complexes. हमने लास्ट वीडियो में assumptions of crystal field theory, what were the basic assumptions of crystal field theory and what were the shapes of d orbitals, इसके बारे में बात की थी. आज हम बात करेंगे कि क्रिस्टल फील्ड स्प्लिटिंग ऑक्टाहेड्रल कॉम्प्लेक्सेस में कैसे होती है. सपोज मेटल आयन इज प्रेजेंट इन एन ऑक्टाहेड्रल कॉम्प्लेक्स एंड मेटल आयन इज प्रेजेंट इन द सेंटर like M and 6 ligands are present at the corners of the octahedron. 2 ligands are present on x-axis, 2 ligands are present on y-axis and 2 ligands are present on z-axis, which is towards the observer. Suppose so this is the octahedral complex, and in octahedral complex what happens if you have remembered about the shapes of d orbitals. Shapes of d orbitals, 3 orbitals are of the same nature in which electron density is present in between the principal axis, and 2 orbitals are of same nature which are having electron density on the principal axis. Those orbitals were dz square and dx square minus y square. Okay, what happens when 6 ligands approach to the central metal ion? When 6 ligands approach to the central metal ion and the electrons are present in the d orbitals of the central metal ion, now the interaction between the ligands which are approaching on the principal axis, these 6 ligands are approaching on the principal axis, and those orbitals which are having electron density on the principal axis, those orbitals like dz square and dx square minus y square, the extent of interaction is maximum in those orbitals which are having electron density on the principal axis and the ligands. So out of these 5 orbitals, dx square minus y square and dz square, these are having electron density on the principal axis. As a result, the extent of interaction is maximum, and we know that like charges always repel each other, and these ligands are of negative charge, or these are negatively charged ligands, or this can be neutral molecules. In case of neutral molecules, these are having negative dipole which is directed towards the metal ions. So when ligands approach to the central metal ion, 2 ligands whose electron density is present on the principal axis, they will show maximum interaction, and due to like charges the repulsion will be there, and due to that repulsion energy of the system gets raised, and this energy raised is larger in comparison to other set of 3 orbitals which are having electron density on the principal axis. So in this diagram you will be able to understand, suppose this is the case of free metal ion that is not surrounded by any ligand. So these 5 d orbitals are of the same nature, these are degenerate in nature. So and when ligands approach to the central metal ion, and we assume that the field around the metal ion is symmetrical, it means the electric field of the ligands that is affecting the central metal ions, that is affecting equally the system. So the energy of the system gets raised, and we say that these 5 d orbitals are again of the same nature. And what happens when there is complete octahedral geometry? 6 ligands are present in the surrounding of the metal ions. What happens? These 2 orbitals, dx square minus y square and dz square orbitals, these 2 orbitals, these are called doubly degenerate orbitals. These are showing maximum interaction with the ligand, so their energy gets raised. So these are of higher energy level, and other 3 orbitals, these 3 orbitals are called T2g, triply degenerate orbitals. These are called T2g set. These 3 orbitals whose electron density is in between the principal axes, whose interaction is less in comparison to Eg orbitals, those 2 sets of orbitals. So In octahedral complexes, the degeneracy of the d orbitals gets split into two energy levels. One is T2g level and other is Eg level, and in this diagram, this gap between Eg orbital and T2g orbital, this gap is called crystal field splitting, and this crystal field splitting is assumed as 1 delta O, or you can take it as by another parameter, that is 10 dq, and this crystal field splitting actually depends on many factors like oxidation state of the metal ions, in which d orbitals electrons are present, and this can also be affected by geometry of the particular complex, whether that is tetrahedral, octahedral or square planar. So it is dependent on many factors. It also depends on nature of the ligand. So this crystal field splitting, this 1 delta O, and what is this? This is minus 0.4 delta O. This is the stabilization factor if the electron present in any of the T2g orbital, and plus 0.6 delta O. This is the destabilization factor if any of the electron is present in any of the orbitals in T2g level. How it comes out? We can calculate this minus 0.4 delta O. Okay, these three orbitals, if we consider barycenter rule or center of gravity rule, so that the average energy of the system remains constant, in that case the decrease in energy for these three set of orbitals, for these three orbitals which are lying on the lower axis, the decrease in energy for these three orbitals will be exactly similar to the increase in energy for these two orbitals. So stabilization factor for these three orbitals will be calculated as 2 by 5 delta O. 2 by 5, because that is equal to these two orbitals which are of higher energy, and it comes out to be 0.4 delta O. So the stabilization factor for these three orbitals will be minus 0.4. Why minus? Because the system is having lower energy in comparison to in comparison to Eg, that is having lower energy, and due to this lower energy it is more stabilized, and we will use minus symbol for this. This is minus 0.4 delta O, or in terms of dq we can say it can be minus 4 dq. We can also use minus 4 dq. This is stabilization factor if electron present in T2g orbital. And in case of Eg, how can we calculate? These two orbitals are destabilized in comparison to these three orbitals. So this can be calculated by 3 by 5 delta O, which comes out to be 0.6 delta O, and we use plus for this because this is destabilized in energy, it has a higher energy. So dear students, when a particular metal ion is present in octahedral complex, 6 ligands are present. Due to the presence of 6 ligands and due to different orientations of d orbitals, whether that is dxy, dyz, dzx, dx square minus y square and dz square, depending on different orientations and depending on number of ligands, depending on a particular geometry, degenerate d orbitals gets further split into two energy levels. One is T2g, another is Eg, and in T2g, remember, stabilization factor is minus 0.4 delta O, and if electron present in Eg orbital, destabilization factor is plus 0.6 delta O, and in terms of 10 dq, this crystal field splitting gap is 10 dq, and this crystal field splitting gap depends on many factors like oxidation state, nature of the ligand, and in which d orbitals the electrons are present, and the geometry of the complex. Okay, dear students, after understanding this crystal field splitting, in my next video, I am going to discuss with you about crystal field stabilization energy. We will calculate crystal field stabilization energy for different cases like D1, D2, D3, and depending on nature of the ligands, we can also calculate CFSE. CFSE can be different depending on complex to complex, it can vary. Okay, dear students, keep watching this video. Stay with me on my YouTube channel. Please like the video and share the video and subscribe this channel. We will meet in next video with CFSE for different complexes. Thank you.